Okay, so before we jump into things, I want to show you in the grade book. So you still have kind of all your old online quizzes that you can kind of see how you did in each individual one and learn smarts. But since we're not having any more of those, you kind of put your grade up and kind of that's what's being weighted and factored into your grade. What your Learn Smart category grade was with the lowest dropped, and the online quiz with your 3 lowest dropped. Okay, so that's what the grade book might look a little bit different there, but it still has kind of all the old assignments, so you can still see, go back and look at them or see exactly how you did. I also, I don't know if we pulled up the YouTube page. Look here, right? Let's go to playlists. Oh, here we go. So if we go down here, I put in yesterday with my other sections, I did some additional linear regression examples. It's really the same stuff we went through, just with different data sets. So if you want to take a look at that, that'll be up there. I'll also, as I'm working through the practice exam problems in here, I don't know if we'll get through all of them. So I'll be posting what we do in class, but also me working through some of the other problems from the practice exams from my other sections as well. So start seeing a lot of kind of videos, even on the days we don't have class, get posted there, which is just me working through more of these practice exam problems, which today I'll kind of start with questions if anybody has them. Otherwise, we'll probably start with this practice exam B, or kind of final exam practice for this semester. Any questions that you would? When? So the exam will be available next Monday through Wednesday. So we'll do technically Monday would be our last class, so I'll still be here to do some review, answer any questions. So I kind of would expect you probably don't want to do it before that class on Monday, but it will be open Monday all the way through the end of the day. Wednesday, you can get on any time and do it. You'll have 2 hours once you start to complete. I think I said last class, but there'll be roughly 15 multiple choice and kind of 2 short answer. I said roughly, I think there's exactly, but I don't want to mix it with my other class. So there's 15 multiple choice, I think, and 2 short answer that have multiple parts to them. One of the short answer, I'll kind of tell you ahead of time, is going to be some linear regression stuff. And the other one's likely going to be one of these different situations where we're doing some hypothesis testing for difference in means or difference in proportions. Yeah, so that is the date. Will be kind of that Monday through Wednesday. Any other questions before we kind of get started here? I'll try to keep an eye on the chat. So if there's specific problems that you have questions on, don't feel like you can't kind of speak up even after that. This first might go over. But we'll kind of start going over some old stuff. So we've been doing a lot of linear regression. Maybe we'll get a little bit of that at the end of the class, but for now, we'll kind of start with question 1 and kind of work from there. So let's say we've got the average age of CEOs, and we want to know whether or not it's been increasing in recent years. So in 2010, we had a sample of 30 CEOs. We have their kind of sample age or their average age. We have this sample variance we found in 2010. And then in 2016, we looked at 25 CEOs, so that's our sample size. We find a sample mean age of 50 and a variance of 25. So this is one of those in which we only have, we have sample means. We're thinking about the difference in sample means, right? The difference between 2016 and 2010, right? Where group 1 is 2016, group 2 is 2010. So kind of the newest years minus the oldest years. Anytime we only have sample variances, is kind of a reminder, if we go to that formula sheet, probably don't need to have it zoomed in this much. There we go, so we can see everything. So we've got 3 different confidence interval equations, 3 different test statistic equations here, and we're looking for the difference in means, but we don't have population variances, we only have sample variances, okay? So before we even jump into this one, just something I think that'll be helpful as you're kind of studying for the exam would be what I'm about to show you. So once the dot cam catches up to us here, we'll kind of set this up. Okay, so we're doing hypothesis testing and confidence intervals. We have a couple different types of examples. So one is that we have 2 sample means, We're looking for the difference in those sample means, but we have their population variances, right? We somehow know their population variances. Under this scenario, we can use that standard normal or the z-tables. Okay? We also have examples where we're looking at the difference in proportions, right? So anytime we see proportions, we should be thinking I'm getting to use that standard normal or the z-tables. Okay? So these are the two scenarios in which, on this kind of upcoming exam, we can use that standard normal distribution. The other scenarios that we have are when we're looking at the difference in means, but all we have are sample variances, right, for the two groups. In this scenario, we use that student t distribution. We can also look at the average difference, in which we only have the variance for that difference variable, the sample variance. So we'll use the student t as well. And then the last one, although we don't really kind of explicitly do like hypothesis testing and finding p-values, is when we have that coefficient estimate and we're also given the standard error. Right? So these are kind of 5 different scenarios, although this one's kind of a little bit different in that we're not doing a whole lot of hypothesis testing kind of stuff with it, but still behind the scenes, you know, that's what's going on when Excel is giving us that output. We've got our matched pairs or our sample difference, and then kind of our original 3 where we're looking at the difference in means, known population variance, only have a sample variance, or if we're looking at proportions, we use that standard normal as well. So this might be something good to have written down kind of as you're studying, as you go into, you know, maybe have it with you when you go to the exam, just kind of a reminder to yourself. And I'll point out in the formula sheet that it kind of reminds you of this as well, because sample means where I have population variances, it tells me use that z table. Proportions, use the z table. Sample means only sample variances, use that student t. Matched pairs, use that student t. Oh, I'm never going to remember this. Letting the slides catch up in class here, or the screen, I should say. Maybe. There we go. So as I was saying, your formula sheet reminds you of this. So if you notice, when we have sample means and known population variances, z-table, proportions, z-table, sample means, only sample variance, use that student t. So this first problem, we only had sample variances. So we know that when we're looking at a confidence interval, we're going to be using this equation right here. Right? Well, we were given the sample means, the sample variances, and the sample sizes in the problem. So it's really just a matter of plugging those in. The only thing left to do would be to find this, you know, t value. Right? So what are we doing here? Well, we've got the 95% confidence interval. So if I've got the 95% confidence interval, my alpha would be what? Shouldn't be too bad at this point. 95% confidence interval, alpha is, yeah, 0.05, right? The area outside the confidence interval in decimal form. So what we're looking for, kind of think about with this student t distribution, is this t value such that the total area outside of our interval, right, in the tails, the total area is alpha, which means we have alpha over 2 in each tail. Right? In this case, alpha over 2, 0.05 over 2 is 0.025. Right? So that's a little bit small. Kind of, that's what we're doing there. Right? We've got our alpha. We know that's the total area outside our interval. That means half of alphas on each side. So 0.025, and I think we were told to assume the degrees of freedom was 46, right? So this is one of those where if you only have sample variances, right, we should be using that really complicated formula. I told you that's just an exercise in mathematics or computation. So I don't want that to kind of trip you up. So I give you that assumed true degrees of freedom. Right? So from here, we're just looking up that t value. So we'll go to our student t table, zoom in so we can actually see something. We wanted the area of 0.025 in our tail at a degrees of freedom of 46. So I'm going to scroll down here. 0.025, degrees of freedom 46, 2.013. Okay? So that's going to be, oops, sorry. That's going to be that t value that we plug in here. Okay? So really at this point, it's just a matter of writing everything out in the context of our example. So I'll leave this up here as we kind of work through this. Right. So the first thing I was looking at was the difference in the sample means. So group 1 was the newest years. They had a sample mean of 50, minus the sample mean from the first group, which was 45. Add to get my upper bound, subtract to get my lower bound. We've looked at the value of 2 point, and I already forgot, I think it was 0.13. Does that sound right? Yeah, 2.013. That was that t-value we needed. Okay. So go back to practice exam B. So 2.013. Then here, we multiply by the square root of each group's sample variance. So 25 divided by, oh, the sample size ends up being the same here. So that's kind of nice. We've got the sample variance of the second group is 36, and their sample size was 30, right? So that's just me writing out this formula, right, in the context of my example, okay? Now, one thing that I want to point out here is if I'm looking at these different confidence intervals, remember, what I was really looking at, the statistic I'm interested in is the difference in my sample mean. So I can kind of think about this as my sample difference, and I'm building my confidence interval around that value to tell you kind of what the possible values are for the true population difference. Well, I found a sample difference of 5, so 5 should be smack dab in the middle of my confidence interval. So if I start looking at these, D doesn't make any sense here. I think the rest of them, it looks like 5 is right in the middle of all these. So I can rule D out, but A through C are still potential candidates until I go through and just enter this into my calculator, okay? So I'll work along kind of with this today. So let's see, we end up getting 2.014. So if we end up doing this computation, if we can get it entered into our calculator correctly, we should get A as our answer. Okay. Any questions about how to approach that one or anything that I said there? Okay. So we've got our confidence interval. If I go down here, so what would the test statistic be for the following hypothesis test? Well, it doesn't matter what type of tailed test we have. We always compute the test statistic the same way for the specific example. So we're looking at the difference in sample means, and we only have sample variances. So when I go to my formula sheet, I've got my 3 test statistic equations here. Here's one for proportions. I'm not doing that. Here's the 2 for sample means, and here's the one where I only have sample variances. So whenever we're doing test statistics here, it's really just a matter of plugging our values in from the information we were given, right? Even in doing the confidence interval, you can see we had that sample difference, right? We already talked about that sample difference there was 5. And then the standard deviation of the difference in our sample means, well, we're using that in our confidence interval as well. So we'd really just be plugging in these same values into the denominator here. Okay. So one thing I want to point out is when we're looking at this test statistic equation, I'm just going to write it out here so we can see it. This denominator, right, represents the standard deviation of the difference in my sample means. Notice it's got variances and sample sizes in it. Those are always going to be positive. When I'm calculating a standard deviation, this denominator in every test statistic, my denominator is positive, right, because it represents a standard deviation. Well, that means that the sign of my test statistic is really dictated by the numerator, right? What sample difference did I find? And that's because we're always using this assumed true value of 0. So if I found a negative difference, that's to the left of 0. If I find a positive difference, that's to the right of 0. Our test statistic is telling us how many standard deviations away from this assumed true value am I? So if I find a negative sample difference, my test statistic will be negative. If I find a positive sample difference, my test statistic will be positive. Here, when we plug those values in, we have this positive 5 difference. So we know our test statistic should be positive. Okay. So when I'm looking at these potential answers, right away I can rule out C. Okay. I believe if I do this, I'll probably get 3.37, but I could be wrong on that. Let's go 1 plus 36 over 30. Yep. So if we plug all those values into that test statistic equation, right? Just plug in my sample variances, my sample sizes here, my sample means. I should get 3.37. So on this one, really, once I kind of help, once we identify the correct test statistic, from there, it's just a matter of plugging those values in and getting it entered into our calculator correctly. Or if you're using Excel, I guess you can kind of enter that equation into Excel correctly. Okay? Yeah.
So the rest of the equation is what we already did in the previous problem at 25 or 25.
I mean, yeah, I was going to say, if you want to think about, right, these were our sample variances before and our sample sizes, because really here we're doing the same thing. We're dividing by the standard deviation of our difference in our sample means to create our test statistic, right? To determine how many standard deviations away we are. In the confidence interval, we're multiplying by the difference in our, the standard deviation for the difference in our sample means. Because here we're saying, well, I need to go this many standard deviations to the left and right. Well, if I need to go 2.013 standard deviations, well, then I multiply 2.013 by the standard deviation. And that's how far to the left and right I go. So we've got kind of similar components in each of these because they're really doing similar things. And I'll try to kind of draw that together because I started grading those fourth Excel assignments. So I've looked at a couple of the responses, but and hopefully I have those done by the end of the day. But I'll make that connection, something that's related to that assignment with what you're talking about. The fact that there's similar components in the test statistic and our confidence interval. Yeah, so that's really the same thing there for plugging those values in. So what if I wanted to find the critical values? All right. So I've got this test statistic, and now I'm looking for my critical values. Well, I've got kind of my benchmark 90, 95, 99% confidence levels. If I look up here, what kind of hypothesis test am I doing? Well, if I look at the alternative hypothesis, the sign tells me the type of test. So I have a greater than sign, right? This difference is greater than 0. So I have a greater than or a right-tailed test, right? So a greater than or a right-tailed test. Oh, I didn't want to do that. I actually wanted to go full screen. So I'm thinking about with my critical values, I'm trying to find the t-value such that, right, my critical value gives me the area of alpha in this tail. So the different alpha values we wanted were what? 0.1, 0.05, and 0.01. So I'm going to have 3 different critical values. But remember, just like the standard normal, the student t-distribution is centered around a value of 0. So for a right-tailed test with these really small areas to the right, these small alpha values, my critical values will be positive for a right-tailed test. So if I look at those potential answers, right away, I know it has to be A or C. If I remember these principles about what we're doing with hypothesis testing or linear regressions, a lot of the time I can rule out a lot of the answers for these multiple choice questions, right? Which makes it more likely I get it right, which is how it should work, right? The more you understand the principles, the more likely you should be to get the question correct. So maybe go through it, and when you're setting these up, think about what you can rule out pretty quickly. And for us, that'd be B and D here. We know the critical values have to be positive. Now, the second thing to remember is I'm dealing with a student t-distribution, right, as we kind of have worked through these examples, and we have an assumed degrees of freedom of 46. So the first thing that I'm going to do is I'm going to look at a degrees of freedom of 46 and an alpha or area in the right tail of 0.1. Right? So we go to my standard normal table, not standard normal, sorry, student t table. We got assumed true degrees of freedom of 46, and the area we want in the tail is 0.1. Right? So we go down here, 1.300. Okay. So if I'm going to kind of build this, and then I'll blow it up here in a second, but as we're looking these up. So the critical value of 1.300 corresponded to that alpha of 0.1, or the kind of 10% significance level, right? Or 90% confidence, if you want to think about it that way, right? So if I think about here's my significance level, here's my level of confidence. The rejection region would be the area to the right, right, or kind of going into the tail. The next alpha I wanted was 0.05, so area in the tail of 0.05, degrees of freedom 46, 1.679. Here's my rejection region. And then the final one, I wanted the area of 0.01. So I'll scroll down here, degrees of freedom of 46, 2.410. and my rejection region is the area to the right, right? So really, I just have to go to that degrees of freedom and look up the 3 columns that correspond to my 3 alpha values, okay? Any questions on kind of that process before we keep moving here? So I've got my 3 rejection regions. You good with that? Okay. So we've got our 3 rejection regions. The next thing we would need to know is, you know, we've kind of answered this question, all right? We just found these 3 critical values. But now we can think about, okay, at that degrees of freedom, you know, what if I found the test statistic to be 2.013? Let's assume that was the test statistic, right? What would the p-value and outcome of the test be? Well, before we do the p-value, we'll do the p-value first and then I'll kind of go to the second part. So I told you, I think in the last exam, I wouldn't ask you to do this, right? If we ever have, or using a student t-distribution, we run into a problem with looking up p-values unless we use Excel, because I only have 6 areas in the tail here, right? And that's what that p-value represents. The p-value is, what did I say, 2.013. So the p-value is, if I take that test statistic, so this is my test stat, the p-value is the area to the right of it, right, for a right-tailed test. So here's kind of my p-value. Now I can kind of already see here, I'm in the rejection region, and I forgot to kind of write what these corresponded. So this was the 5% or the 95% confidence interval, 1% significance, or 99% confidence. So I'm in the rejection region at the 90 and 95% level, so I'll reject here. My test statistic isn't quite in the rejection region at the 99% level, so I would fail to reject there. Right? So if I'm asked, you know, do I reject or fail to reject at certain levels, well, I could have made that decision just based off my critical values. But if I'd asked you to find that p-value, the area to the right of 2.013, we've got a problem because, you know, there's only 6 different t-values at a degrees of freedom of 46 I can look up. So what I'll do, I won't expect you to ever put kind of the p-value in a range. So for instance, let's say the test statistic I found was 1.5. So it was in between these 2 values. Then I know the p-value is somewhere in between these 2 areas, right? 0.1 and 0.05. If I ever ask you for a p-value with a student t, I'll give you exactly one of those numbers. So notice I said it was 2.013. Oh, okay, that's on the table. The area to the right of that, 0.025, right? So that's my p-value. But if I do ask you a question like that, I would give you an exact value that's in that, on that table, right? So my p-value here is 0.025, which if I'm using the p-value approach, right, I only reject if the p-value is, try to get this all on one screen. There we go. We only reject if that p-value is less than alpha. So my p-value is 0.025. That's less than 0.1. So I reject. Less than 0.05, so I reject. But it's not less than 0.01, so I fail to reject, which is the same decisions I made using that critical value approach. Okay. Any questions on that? So it should be what? 0.025, and I forget what the level we were testing at was. The 99% level. All right, so the 99% level corresponds with the alpha of 0.01, so we fail to reject at that level. Okay. Any questions on this? And actually, it was kind of nice. Once we actually found that p-value, we actually knew right away that, you know, we didn't even have to look up what our rejection decision was, because that's the only answer that had 0.025 as a p-value. Now, one thing that I want to kind of point out, so let's assume I didn't give you this. So this is what I do on the exam. You know, if you got the test statistic wrong, you're not going to get the next question potentially right. So like I'm giving you an assumed true test statistic here. Assume, however, that we were using the actual test statistic, right, before I gave you this assumed true value. 3.37 is going to be way over here. We're going to reject at every single level, right? We're easily in that rejection region for every single level. Now, to relate what we're doing with confidence intervals and hypothesis testing, notice at the 95% level, what my confidence interval is saying is these are the values that could be the true difference, right? 2 through almost 8, right? Those values could be the true population difference. So if I do a hypothesis test for any value in this range, I should fail to reject it because it could be the true difference. However, if I do a hypothesis test for any value outside this range, well, those at the 95% confidence level aren't potential values, right? So every value outside this range, I can kind of think about, I would be rejecting those as potential true differences. Well, guess what? 0 is outside this range. I'm doing a hypothesis test for the value of 0, right? So I should be rejecting, right? Because 0 is not in my confidence interval. Sure enough, if I were to use that true test statistic, that's easily in my rejection regions, and I'll end up rejecting, right? So that's kind of what we're doing with confidence intervals. Confidence intervals tell you the range of values that could be the true difference. With hypothesis testing, what it's doing is it's taking one of those values that's either in or outside of that range and telling you how likely it is that value is the true difference, right? So it's a little bit different. It also allows us to do things like with the confidence intervals, because what I'm saying kind of isn't correct in the sense that it's only correct for two-tailed tests, right? Because two-tailed tests line up with confidence intervals in that we can see, we allow that true difference to be in either direction, right? To the left or right of the value that we're looking at. Whereas with hypothesis testing, it allows us to take examples where, let's say, let's say I'm worried or I'm thinking about the average, let's think of a good one here. So let's think about like the average amount of money someone spends on food at restaurants. Well, if we look at 2 years ago compared to this past year, we kind of know what direction that's probably going to go, right? With all the corners. So we kind of already know that difference is going to be a certain sign. So that's what hypothesis testing allows us to do, is do things like not just two-tailed tests, but directional, right? Right or left-tailed. Okay. Any other questions kind of on these first 4 problems we've worked through here? Okay. So I think what I'm going to do, I don't know, if you guys really hate this, feel free to email me or let me know. But I'm probably going to hop around a little bit just because I think that I think it's good to get a dose of hypothesis testing and linear regression. And if you're showing up and you're watching the videos, I think that's good to get a little dose of each one. So we're going to skip ahead and look at some change from hypothesis testing, look at some linear regression stuff here. So let's say we run the following regression, right? I think we've looked at this GPA data set. Yeah, we did. And we have, a bunch of different variables, but let's say I just include these 5. So we've got SAT score of the individual, whether or not they were an student athlete, so that's just a 1 or a 0. Their ranking in high school, whether or not they were female, so just 1 or 0 there, and then how many credit hours they had taken that was factored into that GPA. So you run this regression, and this is like the following output, right? So you might see something like this on the exam, where I give you some output that came from Excel. Well, I blanked out the test statistics here, right? So I think that's one of the following questions. Oh, where is it? Yeah, so it's way down here, but we'll get there. But I put a box over it. So if you are interested, you can move that and see what the actual test statistics are. But I probably would do something like this on the exam where I don't show them to you and ask you to calculate one, and we'll go over that here in just a second. So the very first question is, what is the correct interpretation for the coefficient on the SAT variable? Right? Well, before we even look at the answers, we should be able to come up with this. I don't think it's, I'm always surprised at how maybe sometimes people overcomplicate this, because it's the same pattern every time. The interpretation for a slope coefficient is a 1 unit increase in that x variable causes the predicted value of y to go up or down by whatever the coefficient value is. Right? So here, a 1 unit increase, if we go up, SAT score, it's just your SAT score, so it's measured in points. So a 1 unit increase is 1 more point on the SAT score. If I scored 1 point higher, would increase predicted GPAs, my y variable, by 0.002, right? Holding everything else constant in this regression, right? So when we have multiple x or right or independent variables, then the interpretation we have to throw on at the end, holding everything else constant. Or we can say it at the beginning, either way, right? So here I'm looking for this phrase because I have 5 variables on my right-hand side. I should at some point be saying holding everything else constant, okay? So if I asked you like on a short answer, and I gave you some regression output, and you're interpreting a slope coefficient, right? Somewhere in your interpretation of that coefficient, you should have holding everything else constant. Okay? So holding everything else constant, so we can rule B out right away. Every additional point on the SAT is correlated with a 0.002, if I could spell, increase in GPA. Well, that was exactly what we said. Right? Not holding everything else constant, the average GPA, holding everything else constant, an additional point is 0.8. Where'd that 0.8 come from? Oh, I wish I'd been looking at the wrong coefficient there, right? My slope coefficient on SAT was 0.002 here, so we know that A is the correct answer, right? So that's the correct interpretation. And, you know, it's kind of powerful, right? It's like saying 2 people who are either athletes or not athletes, same high school rank, both female or male, same number of total credit hours, but one of them scores 1 point higher on the SAT score, their predicted GPA would go up by 0.002. Okay? Any questions on that interpretation? I think the next one might be the intercept. Yeah, so what would the next question is, what's the interpretation of the intercept coefficient? So I go up here, here's my intercept, here's that coefficient, right? So the way that we interpret the intercept is always the same. It's if all the x variables are equal to 0, the intercept is the predicted value of my y variable. So if SAT score is 0, the person's not an athlete, or 0, ranked 0 in their high school, which, once again, these interpretations for the intercept will sometimes be very wacky, right? They weren't female, they were male, and the total credit hours in their GPA is 0. So all these variables equal to 0, the predicted GPA would be 0.8. So if we're looking for something that matches up with that, not an individual with the averages, no, the individual with 0 SAT scores, ranked 0 in their high school, everything's 0, then the expected GPA is 0.803. So that was our interpretation that we had said. You know, this is a little bit goofy, this interpretation. I think I've shown you a couple times why, but you know, that is the way in which we interpret it, right? It's our starting point. And then as things change, as things move away from 0, we come up with different predictions. Okay. Any questions on that? Okay. Actually, let me, it's not overly important for the exam, so I guess we'll hold off on that. So if I'm looking at my output, the next question I'm asked is, what's the test statistic for the athlete coefficient? Well, if I go up here, this should be, in my opinion, the easiest question. I guarantee you, I might have 1, I might have 2 on the exam, right? But if I ask you for a test statistic for a slope coefficient, it should be very easy, right? All you do to get that test statistic, right? So if we're trying to come up with a test statistic, all we're doing is, right? Well, we can subtract the assumed true slope, but what did we say our null hypothesis is for all slope coefficients? The null hypothesis is that it's equal to 0. So this assumed true value is always 0, so we might as well just ignore it, right? We're always going to be using the same hypothesis test for these slope coefficients. And then all I'm doing here is dividing by that standard error, which is also going to be given to me in that Excel output. All right, so for this athlete, I think it was the athlete no, I better double check. Yep, the athlete coefficient. All I would do is 0.162 divided by 0.043. Right? Just take the coefficient, divide by the standard error, and you'll get your test statistics. Right? So if you move these out of the way, notice 0.16 divided by 0.04, that's almost 4, right? 0.18 divided by 0.018, that's almost 10, right? So it's just the coefficient divided by the standard error gives you your test statistic for your different slope coefficients, okay? So, you know, you could do that for any of these. I could ask you to interpret this, or to give me the test stat for any of these variables here, okay? Any other questions on that before we keep moving. So I'm going to add some, so I think if I did that right, we got, should be about 4 or just under 4, so 3.7. I'm going to add in some additional questions here, just because we're using this example. I know I've got some more stuff down here, but I want to kind of, I'll save that for kind of next class, because I know there's some other types of questions that I could ask you. So if I'm looking at this output, and I'm just going to give myself some space here to kind of type out some additional questions. Okay. So which of the included X variables or independent variables can we reject the null for at the, say the 90%, or no, sorry, let's do the 10%, this is how I would phrase it, significance level. That's a very possible question I could ask you on the exam. Now, this output is a little bit weird because if I'm looking at this output, which variables can I reject the null for at the 10% level? Same kind of condition applies. I only reject if the p-value is less than alpha. So I'm looking at my p-values here. Which of these would be less than an alpha of, at the 10% significance level, alpha is 0.1. Right? So which of these levels, or sorry, which of these variables can I reject at that 10% level? What's true about all their p-values? They're all pretty much 0. Is 0 less than 0.1? Yeah. So I can reject the null for all these, right? Or, said differently, all of the variables are statistically significant, right? Or they're all significant, I guess, at a 10% level. Or it could have said that I reject the null for all of them. And why? Because, remember, the null is that slope coefficient is equal to 0. If I'm rejecting this null, what I'm really saying is there is a statistically significant relationship between that x variable and that y variable at whatever level I'm looking at, or whatever alpha I'm looking at. So here, all my p-values were 0. So if my rejection decision is that when the p-value is less than alpha, well, p-value of 0 is going to be less than alpha every time. Now, on the exam, I probably would do something like this, you know, give you an example where, you know, I don't know, this one was 0.042, 134, I don't know, give you some that, you know, might be rejected at certain levels, but not others. Right, so if I had something like this, well, now the only variables that I can reject the null for, or say that there's a statistically significant relationship with the x, or sorry, with the y variable. Well, I can't say it for SAT score anymore, right? I can't say it for the female. Only athlete, high school rank, and total credit hours would have a p-value less than 0.1. So I could only reject the null for those 3. Right? So that's something that, you know, I have the exam written, so that might be something good to go over. Right? Or something I very likely could do. Okay. Another question I could also potentially ask is, how much of the variation in GPA can I explain with these 5 variables? Well, that's literally just the interpretation of my R squared, right? It's the proportion of the variation, the y variable I'm explaining with the x variables I included in my regression. So I'm explaining the proportion of 0.27 or 27% of the variation. Right? So kind of knowing how to interpret that R squared, right, as being the percent of that y variable that we can explain with these variables, or sorry, the proportion of that y variable, right? We can look at it either way. We're just scaling it when we look at it as a percentage. Okay. Any questions over anything there? So kind of knowing how to make rejection decisions. I could also do something like this, and I probably wouldn't maybe be quite this mean, because with 5 variables, this would take a little bit longer, but I probably would do it with an example that only had 2 or 3. But here's 2 other questions. So what is the impact, or what is the effect on GPA from 20 additional credit hours? Okay. Well, I know the effect of 1 credit hour, right? A 1 unit change in total credit hours changes my predicted GPA by 0.002. So the effect of 20 would simply be 20 times the effect of 1 unit, or one additional credit hour. So I don't know what 20 times 0.002. So we've got what, 0.04 if I'm doing this in my head correct. Yeah, just double checking my mental math there. So I could ask you something like that. I could also say, what's the predicted GPA, right, for a student with 1,000 SAT score, is an athlete, ranked 30th in their high school, male, and has taken 40 credit hours. Right? So all I'm going to do there, right, my regression equation it should look something like this, right? I'm predicting GPA using that intercept plus the coefficient on SAT times the SAT score variable plus the coefficient, I forget the second one, I think that was athlete, right? The slope coefficient athlete times the athlete variable. Same thing for all the other variables I included. So now that I have estimates for these coefficients and I have this hypothetical person, it's just a matter of plugging these in. Multiply the coefficient by the hypothetical value for X and then add them all up. Right? So if I'm looking here, all I would do is take 0.002, multiply that by what they got in the SAT, so 0.002 times 1,000. Wish I could get this all in kind of one line here. I'm going to cut this so I can easily show this to you guys. Okay. So all I'm going to do is take that coefficient on GPA, 0.002, multiply that by 1,000. Add to that the coefficient on athlete, 0.162. This person is an athlete, so they would have a 1 there, right, for that binary or that dummy variable. High school ranking, well, minus, because it's a negative sign on that coefficient, 0.003 times, they were 30th in their high school, plus that coefficient on female, 0.186 times, well, this is a male, so that female variable would be 0. Add into that the coefficient on total credit hours times the total number of credit hours this person's taken, and that should give me my predicted GPA. Oh, what? I forgot one thing. So I got all my coefficients multiplied by the value of the variables, but I still have to add in that intercept, right? I should have at the very beginning had 0.083 just added in there because my intercept always gets added into that prediction. Okay? So at this point, it's just a matter of really getting that entered in to our calculator. And I'll give you the value here so we can double check in just a second. So we end up kind of getting this entered into our calculator. We should get what, 0.2955, right, as the predicted GPA there. So that could be another question on this. Like I said, I probably wouldn't do something like that, maybe with only, 2, 3, or 4 variables. 5 here just gets a bit much. But even if I did have a lot of variables, I might do something like this if a lot of them end up just being 0, because that makes the math a little bit easier. But these are all potential questions that I could ask regarding linear regression. Okay. Making predictions, finding the, which variables are significant, finding the increase in the Y variable from not just 1 unit, but multiple units of a specific variable. Those are all kind of fair game. Any other questions on that? Okay. I kind of want to save some of this for on Friday. So one thing that, just to kind of reiterate, and and I kind of already mentioned this at the beginning of class, but if I did want to look up p-values for these slope coefficients, like let's say for some reason I wasn't given the p-values in my output, I could actually take the test statistic, right? I know how to calculate my test statistic. And I could look that up at the correct degrees of freedom. We kind of aren't doing that on our own because the degrees of freedom is a little bit different and I didn't want to dive into that subject. But also we're always kind of, given the p-value from Excel, but just in case I did want to look it up, I should always be using a student t-distribution, right? At the very beginning I said for these coefficients, we use a student t-distribution. And this is always our null hypothesis. So it should always be a two-tailed test from a student t-distribution, okay? So I'm thinking about if I was looking up the p-value, this should be a student t-distribution, and it should be always a two-tailed test where I'm assuming that the value is equal to 0, at least for what we're doing in this class. You can do right and left-tailed tests, but they're not the most useful or common that we would ever want to do that, okay? All right. So I think I might stop there. So got a couple minutes left, but I think what I want to do is, so hopefully, we used it in one of the examples, but hopefully you can kind of see on this formula sheet, if you want to print this out or write next to it, like here's what we use when we have known population variances, sample variances and sample means, sample proportions, like write those next to your test statistic and confidence interval equations so you can quickly and easily identify them. And then down here, you kind of have a confidence interval and a test statistic for those matched pairs examples, okay? So those are all the formulas you should need. I guess if you want to think about one formula you could add, maybe I'll add it into the formula sheet. It doesn't really help you a lot, but it's basically going to be this guy, but in general form. So if I ever want to make predictions about y, right, I'm going to take whatever the estimate is for the intercept, add in the estimate for the first coefficient times the value of that first variable, second coefficient times that second variable, right, out to as many variables I included on that right-hand side. I guess this is technically an equation you might want to have. Also, the test statistic, I think this one's easy to remember. That's probably why I left it off the formula sheet, but I can actually go in and add it on there, which is the test statistic for any of these slope coefficients is simply that coefficient divided by the standard error you're given from Excel. Okay. So those might be two additional equations you might want. I'll put them in that formula sheet and get that updated this afternoon up on Canvas. Other than that, I think we'll kind of stop there for today. Like I said, I will, hopefully have kind of gotten through all those fourth Excel assignments by the end of the day. So those should be graded. If you did, I saw a lot of people didn't turn something in. So if you didn't turn in that fourth Excel assignment, you really need to make sure you do that fifth one, because if you start, missing multiple assignments, I only drop the lowest. So if you miss 2, one of those zeros is going to count, right? So just kind of from what I saw in terms of who turned it in, a lot of you hopefully will be getting that fifth Excel assignment turned in by the end of the week. Okay. All right. There's no questions for me. We'll kind of end it there, and I will see you guys on Friday. We'll just